second circuit of the chip of yesterday. Yesterday we did the multiplier connections and we saw the result. We plugged in two DC signals and we got the product of their differences divided by 10 volts. Today we will look at the squaring and frequency doubling, and this will require an output of the signal squared over 10 volts. So let's wire it up. We have pins number 1 and 3 shorted, and we're going to inject the signal into pin number 1. We have the differential output plus 15 minus 15 and ground, and the output will be right over here. We can take our oscilloscope probe and let's take a look at some waveforms. We're going to use the oscilloscope's function. I adjusted the frequency according to the model results that are in the data sheet as well. They look something like this. They made a circuit on multisim. I didn't put the voltage divider, but I fixed it from 1 kilohertz to 10 kilohertz, and those are the results we're supposed to get. So we got the same thing over here. And if we just want to do something real quick, let us put them in the same scaling factor and get that to 1, 2, 5, 1 volt. So I want them to be both recognizable. Let's fix that to about 200 millivolts, and this one 200 millivolts as well. So we can see that the frequency of the output is smaller than the frequency on the input. The amplitude is smaller, and if we had to go, so this F1 in yellow is 10 kilohertz. If we go to F2, and I should be able to put to measure source channel 1, channel 2, add delete frequency. So over here we now have 20 kilohertz. So it is saying, as it implies, it is frequency doubling, squaring and frequency doubling, and the amplitude is going to be smaller. I think I nudged a few things. So the frequency is going to be smaller. The frequency is going to be double, 19 kilohertz versus 10 kilohertz, but the frequency is going to be divided by 10 because of the internal Zener diode. So that's the squaring and frequency doubling circuit. Take a look at the second circuit, which is the bounceless frequency doubler. Of the charger. There we go. So that's the signal we're getting on the output. And we can see that there is a little bit of a phase difference. Can we measure that? Phase difference. Source 2, add, period. Mean, nope. We cannot. But the frequency is doubled. That's good. And there is a bit of a phase difference between them. Let us see what happens if we play with the input potentiometer without making too much movement. It's only playing with the amplitude. Let me try to change the capacitor value. Right now I have 0.47 microfarad. I'm going to remove the capacitor and I'm going to put in a 0.01. So that's a good difference, and the phase is also different between them. Let's see. Yep, there is a phase change between the two signals. Very interesting. And what else can we do? What happens if we put period? No, that's going to be useless. Min max peak to peak, we don't want that. We don't care about the mean. Okay, so I guess that's what's going to happen with the bounceless frequency doubler.